Hey everyone, welcome back to another fun and exciting geometry class. Today we are going to be in lesson 2.17. Now I know we just finished up a test, and usually when you finish up a test you go to a new chapter, but in this book that doesn't always happen. So this is kind of a little bit different. We're just picking up where we left off, 2.17. Today we're going to be talking about distance, and I think we're going to get in 2.18 as well, parallelograms in the same lesson. We'll see how it goes, but I think that's probably what will happen. So today we're going to be talking about these three different types of distances. The first distance is distance between 2 points. So if I have a point here and a point here, distance is the amount of space in between these 2 points. So if I take this line and stretch it out, that's distance. The amount of space, the amount of time that it takes me, the amount of inches, the amount of any unit that I decide, whatever it is, between the 2 points. So my distance between these 2 points, that's something that we dealt with in algebra class. That's something that we dealt with in trigonometry. But here, it's more the concept that we're dealing with. And we're not going to use a distance formula. We're not going to figure out the distance. We want to talk about the concept of distance, the idea of what that looks like. Well, the concept of distance is the space that's between 2 points connected by a straight line. Now that's the shortest distance. That doesn't mean that it's the only distance. You could go in a semicircle if you wanted to. You could go in just any whatever pattern that you want to go in, and you finally end up there. Okay. Now, distance is just like I said, the amount of time, the length, the amount of units, whatever you're measuring with, inches, miles, feet, centimeters, doesn't matter. The distance between 2 points is the length of a straight line. Now in geometry, they're not talking about the curvature of the line, okay? They're not talking about that. They're talking about the straight line. This is the distance that they're talking about in geometry. 2 points, straight line, that's distance. Okay. This is kind of like when we would use a map, things like that. The distance between 2 points is a straight line. Number two, the other thing that they talk about in this lesson is, well, what if I have a point outside of the line? Well, your distance to the line, okay, now you could go this way if you wanted, you could go this way if you wanted, you could go this way if you wanted. But the distance in geometry is a straight line again. It is what kind of line does this make? It's a perpendicular line to the given line. So the shortest distance between a point and a line is a perpendicular. Now, what happens if I have, I'll kind of do this, and I have two parallel lines? Okay, so I want to know, what is my distance between these lines? Well, the distance is again, a perpendicular line, a perpendicular to the 2 points in the line. And that's all in your book in lesson 2.17, distance. Page 90 and page 91 is where you'll find all that information. You can look it over if you want to, but there's basically three different concepts of distance that we'll be using in geometry. Distance between 2 points, distance between a point and a line, and distance between two parallel lines. That was easy, right? Let's go on to lesson 2.18, page number 93. All right, page number 93, we start talking about shapes other than the triangle and the circle. We've already talked about those two. But now we're going to be talking about more shapes, and these specifically are parallelograms and quadrilaterals. Quadrilateral is kind of the big umbrella name for the shape we'll be talking about. A quadrilateral is any shape, any closed shape that has four sides. Okay, so quadrilateral makes sense, right? 4 quadra, and then lateral means side, and so 4 sides, so quadrilateral. Now, specifically, what we're going to be talking about in this lesson on page 93 is the parallelogram. Certain types of quadrilaterals that are parallel. Let's take this for example. So I've got a line here, and I've got a line here. Those lines are parallel to each other. But for this to be a parallelogram, this side must be parallel to this side as well. In other words, these two, the top and bottom, must be parallel, and the left side and the right side must be parallel. If all those things are parallel, then I have a quadrilateral, but I have a parallelogram. One way to prove that, because we prove things in geometry, it's kind of what we do, is to prove that all of these are right angles. If they're all right angles, then by, definition of what a right angle is, we're going to get 180s right here. So 90 plus 90 means we're turned back in the exact same direction. And so there's different ways to prove these things are true. So that's a parallelogram, and that is a certain type. That one's called a rectangle. The reason that's called a rectangle is because it had 4 right angles, but not all of them need to have 4 right angles. There's other types of parallelograms. Let's say that this line over here is not a 90-degree angle. Let's say it's that. Well, we could still have a parallelogram if that side is parallel and if this bottom side is parallel. Now, I didn't draw it perfectly. Didn't quite connect for me. I can connect it. Yeah, there we go. A little bit better. And but this is a parallelogram as well, because look, parallel to that. Those two sides are parallel, and then look over here. Left side parallel to right side. So if top is parallel to bottom and right side is parallel to left side, it's a parallelogram. Now, if you look here, we don't have right angles anymore. That's not a right angle. But look at this. This angle here equals this angle here. And this angle here equals this angle here. So, some interesting things about a parallelogram. Is the opposite angles are going to be equal. And why is that? Again, we have parallel lines. Look at these parallel lines right here. And then what's happening right here? They're being cut by transversals. Well, if the transversal is parallel to, so if these transversals are parallel, and if these lines are parallel, then look, these are going to be corresponding. Let's call this angle 1, this angle 2, this angle 3, this angle 4. Number 1 and number 4 are going to be equal because they're exterior alternating. And you say, no, they have to be over here. It has to be over on this side. Well, it doesn't matter if everything is parallel. It doesn't matter if, where they are. We could have another one and another one and another one. If they're all parallel, it doesn't matter where the angles are. They're alternate exterior. And then this one, these are the inside ones. These would be alternate interiors. And so in other words, so if this one was here, basically, so if you took that and moved that over, they're alternate interior angles, and so they're equal. And so that's some interesting things here that we find about parallelograms. And really most of it's built on the whole idea of the parallel lines and the transversals that we've been talking about in earlier chapters. A couple things that are very important. The side that it's sitting on. So in this case, this side right here. This side is called the base. Okay. The other important part of this is what's called the altitude. The altitude is the distance, so this would be the altitude. okay? And the altitude is the distance from the base to the top. Now, we just talked about distance a second ago. What is distance? It's from, again, these are parallel lines, so it's a perpendicular. That's why this is not an altitude, because it's not perpendicular. It has to be this perpendicular line. The line, because again, we're measuring distance, and altitude is a distance measurement. So when we measure the distance between the base and the top, so kind of the height or the altitude of the shape, we're going in a perpendicular line from the base. It has to be a straight line to be perpendicular. So perpendicular line to the base will give us the altitude of the shape. A few of the special types of parallelograms that we have here, you can see them in your book, page 93, is a rhombus. A rhombus is a parallelogram having two adjacent sides equal. And so, like, if we could prove that, and this one is not, let's say that this side equals this side. Well, in this case, it does not, so that's not a rhombus. But if I wanted to make a rhombus, I would come over here and I would say, okay, this has to equal this. And if it does, then I have a rhombus. And again, it's not perfect, but it's close enough. And so if I say, okay, this side equals this side, then that's a rhombus. Okay, so it's a parallelogram with two sides equal. Now, one thing that you might be thinking is, what about a square? Squares have equal sides. All four sides are equal. Well, a square is a rhombus. It's a special type of a rhombus. A square is also a rectangle. Well, what's a rectangle? It says on page 93. A rectangle is a parallelogram that has an angle as right angles. So all four angles are right angles. Well, in this case, these are all right angles. All these sides are parallel. A square is an interesting one because a square meets every single qualification. A square is a rectangle, a square is a rhombus, a square is a parallelogram, a square is a quadrilateral. A square is all of the above. Okay, not all rhombuses are squares, but all squares are rhombuses. Okay, not all rectangles are squares, but all squares are rectangles. And so that's something interesting with the square. The square meets all of the qualifications. All right, page 93, we have theorem 19. Okay, theorem 19 says the opposite sides of a parallelogram are equal and the opposite angles are equal. I've already talked about that. I kind of let theorem 19 out of the bag just a little bit when I told you up here that this angle equals this angle. Okay, the opposite angles are always equal in a parallelogram. Okay, and I showed you why too. So again, I kind of let the cat out of the bag, but it is what it is. Corollary 19.1, these are on page number 94, page 94. All sides of a rhombus are equal and all sides of a square are equal. Already talked about that just a little bit. Because if this is equal to this, then the definition of a rhombus says that they have to be equal to this and it has to be equal to this. And the same thing with the definition of the square. They would all have to be equal. Corollary 19.2 says a diagonal divides a parallelogram into two congruent triangles. Now I want to show you this. Let's go ahead and erase some of this stuff, get it out of the way. And I want to show you this right here on this one. So if I take this parallelogram that I have drawn here, and if I take it and I put diagonals in it, basically if I take this corner right here and drag it all the way over to this corner, I cut it with a diagonal. What I've done, and this theorem right here and this corollary 19.3 tells us that this triangle that I have left over, this one right here, is going to be congruent to this one right here. See, I cut it into two triangles. I have one on the top and one on the bottom. They're carbon copies of each other. They are the same thing. They are congruent, and that's well, 19.2. Corollary 19.2 tells us that. And it doesn't matter, and you could do this one too. So we have another diagonal that goes this way, and these ones would be congruent. So this one would be congruent to this one. Here's something that's also interesting. This one is congruent to this one, okay? And this one is congruent to this one. They're all congruent. Whenever you draw different multiple diagonals through it, they all end up congruent. Corollary 19.3, parallel lines included between parallel lines are equal. So parallel lines included between parallel lines equal. In other words, here's what that looks like. Let me just get a new one. So parallel lines, and parallel lines included inside of these have to be equal. They have to be. And here's the idea of the rectangle forming. Okay? And so what that's saying is that these have to be equal. Those sides would have to be equal. If I have two parallel lines, one top and one bottom, and then I connect two more in there, then they are equal. They must be equal. Corollary 19.4 says that two parallel lines are everywhere the same distance apart. So in other words, this distance is always going to be the same as this distance. Really, 19.3 and 19.4 are pretty similar there. All right, one more thing, and then we'll be done with this lesson. It is theorem number 20. Theorem number 20, and that's on the bottom of page 94. It says the diagonals of a parallelogram bisect each other. The diagonals of a parallelogram bisect each other. So I had the parallelogram there. There it is, and I even had the diagonals in it. But let me get a straight line going. So if I put there and I put another one there, this point right here is a very important point in geometry, okay, for several reasons. But for right now, here's what it means. It means that this piece equals this piece. It also means that this piece equals this piece. So by saying that those are diagonals, we can say that this piece equals this piece, and this piece equals this piece. Very, 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 very important. Now, let me show you something that's kind of cool right here. What we've just proven is we've proved that those were congruent. Remember when I told you they were? Why? Because there's vertical angles right there. So now we have side, angle, side. Okay, we just proved congruency by using corollary number 20. Corollary number 20 says the diagonals of a parallelogram bisect each other or cut each other in half. Okay, all right, that's all I got for you today. I hope you have a good rest of the day. We'll see you later. Bye-bye.